Hello and welcome to Webgains Transform 2020. I'm very pleased to introduce Humphrey to you today. Humphrey is a creative technologist who works exclusively with the product and development teams here at Webgains to build out our machine learning capability. Humphrey is ideally placed to work with Webgains given his experience as a CTO for various e-commerce, trading and leisure travel domains, and he holds a PhD in machine learning. Focused on the application of cutting-edge machine learning approaches to e-commerce data, we will hear today from Humphrey about machine learning and the application of his work with the Affiliate Discovery product.
Hi everyone, and welcome to our session on Affiliate Discovery at Webgains. Affiliate Discovery represents over a year's worth of work in applying machine learning to the large data sets that Webgains has gathered over the years in order for us to be able to build a really special tool to connect publishers with merchants. Before I dig into Affiliate Discovery, I want to just take a second and actually a few slides to go through machine learning in a wider sense in general. So on the right hand side here we have the kind of computer software that you've been using for a very long time on your laptop or mobile phone or any other platform. It's hard coded, so it's designed to do one thing, do it very well, any kind of task, whether it be word processing, acting as a browser, any kind of application like that. So the program, may load data from a separate database, but once written, it will not change unless the programmer makes a change. On the left-hand side here, you can see the real difference, and it's this green module, which typically we call the teacher module, or which learns the error profile of the task. So what happens in a machine learning setting is that the program is able to modify itself over time. We typically say it learns from data. And it learns from data by receiving back some kind of error metric from an external oracle or teacher. And that's what's going on here. So this feedback loop occurs in pretty much every machine learning task you can think of, whether it's self-driving cars to search and recommender engines that we'll be talking about here. And it's the key difference. It's what helps machine learning to learn over time, to automate tasks that would have been previously cumbersome and nigh on impossible to do at scale by humans. So you've probably seen machine learning is cropping up in multiple different avenues, from mainstream media to social media and so on. And why is that? The real enabler has been the mass availability of data. And anything can be data. We don't mean any kind of data. We mean data with very specific metadata attached to it. So it's been curated, typically reviewed by humans starting out. So this is ImageNet. ImageNet was one of the big enablers for computer vision, the application of machine learning to the computer vision domain. So WordNet, which came before ImageNet, was essentially a semantic ontology of heavily focused on English, the English language. ImageNet, if we can see here, is built around the concept of synsets. So these, on the top row here, we have a synset of people. So you've got people in different settings, then you've got human beings in different settings, and all the way down to you get different types of schoolhouses. And what's interesting is we can then feed this tagged data into multiple machine learning models to see if they can learn the intrinsic concept which distinguishes, for example, a schoolhouse from a regular house, what distinguishes a child from a grown-up adult or human being. So data in its own right has become an asset. Companies now regularly capitalize and depreciate that asset, which is a real step change. So in the past we would consider the software to be the asset, but now data is at least as important. In fact, in machine learning, the data is often more important than the software. So let's talk about self-driving cars. So there are many different companies trying to crack that problem. Tesla would be the obvious standout example in that space, but there's many companies, large companies, trying to do it in Europe and the States and China, and many startups as well working on the problem. And again, it's one of the hardest things is the acquisition of data, the acquisition of label data. So here's an interesting application from TU Darmstadt in Germany, where these guys took computer-generated images from I think this is Grand Theft Auto 5. So if you've played that on your PlayStation or Xbox, you'll know all about it. And here we have segmented the image into foreground, background. You've got cars, trees. So you've got moving moving components, static components. And once you've done this, it becomes incredibly easy to generate. It's not super high quality. It's not as good data as actually capturing it from a moving car driving in the real world, but it's still very good, and it's far better than no data. Also, there's an interesting property of generating data like this, in that you can easily change conditions. So on the top here we have a rainy, dull, overcast day, and on the bottom we have a dry sunset day. So capturing different, and this is really important for training self-driving cars. So generation of data has come on in leaps and bounds in the past couple of years. The second thing that's available to really enable machine learning is the wide availability of compute power on multiple different platforms. So whether you're on EC2 with AWS, Amazon, Google GCP cloud platform, or Microsoft Azure, running your own private cloud, and the cost of this has been dropping, as with all things computing, year on year on year. So now you can get GPUs to train machine learning models, particularly neural network models, at a fraction of the price even just a couple of years ago. So data plus compute power is a real enabler for machine learning. We've also seen that there's, the media really got on the bandwagon here. So these, first of all, there was the excitement about machine learning could do, and then, I think we always do this. We wonder, is this what's going to kill us? So, are we looking at killer robots coming in the future? A la Terminator, the Terminator movies, and the truth is, it's probably there's a vanishingly small probability of that. Because we'll talk about what machine learning can and can't do in a second, but in general, machine learning now, there's a real hype and buzz and excitement about it. So people want to know, how can I apply it in my business? How can I use it in my domain or my vertical, which we'll be talking about. The commercial incentives are huge. So these slides don't even capture the last movements in the share price by people like Tesla, Google, Facebook since February, March. But in general, if you're on a platform which is designed to consume content, whether that be video, HTML, static, audio content, it's all about increasing user attention. Sometimes to the detriment of lifestyle or work-life balance. And the average viewing session has increased dramatically on all these platforms over the past number of years. And that's had if you have people sticky to your platform, you can show them more advertisements. It's a linear relationship, and that's exactly what these guys have been doing with machine learning, and in particular their recommendation algorithms. Okay, so a really canonical task in computer vision is the dual task of, can you segment an image into its important constituent parts, label those images, and then tell me what they are. So these are some really good examples, as in high quality. So here we have an image on the left. The highlight on the right for each image indicates where the network is paying attention to the image. Attention is a really important part of most machine learning models. And on the bottom, we have the auto-generated caption for that image. And you can see here it's incredibly precise. So we have a woman is throwing a frisbee in a park, a dog standing on a hardwood floor, so it picked out the detail of the floor, stop sign on a road with a mountain in the background. These are all really, really good. These are all, A+. A group of people sitting on a boat in the water. That's excellent fidelity. So let's talk about this example. So a giraffe standing in a forest with trees in the background. Great. Okay, so that's fantastic. And at the bottom there, that's the paper which generated these examples. However, what you typically don't see, and it's not the papers, it's not the researchers who hold this information back, but again, it's not that interesting from a media perspective to talk about what didn't work, is that machine learning models fail in all kinds of interesting and wonderful ways. So they can do just as badly as they can do fantastically well. So same model, same data. Here we have, for the giraffe image, a slightly separate angle, a large white bird standing in a forest. We have a woman with the O'Neill logo, which is circular on the front of her sweater, a woman holding a clock in her hand. So got completely, you can understand the rationale and the logic for it, but it's interesting to see where it goes wrong. So one of my favorites over here. So this guy is eating a sandwich. A man is talking on his cell phone while another man watches, that's not what's happening. So then you start to, and sometimes introspecting machine learning models when they go wrong can tell you an awful lot about what they're doing. And what we can see here is that these machine learning models are not learning deep semantic understanding of objects in a foreground or background scene image. That's not what they're doing, and this has been proven time and time again. They're not operating at the level that we expect them to, and that's, as humans, when we see excellent results, we automatically impute that machine learning model with far more intelligence than it actually possesses. So I just want to point for balance the good and the bad. That's not to say that machine learning isn't great, because we do think it's great. So here's another interesting task in the computer vision domain. So here you're given just the image with no geolocation data. This has been a challenge that's been around since I think 2004, and there's quite a large data set behind it. And it's able to, cherry blossoms in Tokyo, the neon signs, fake neon signs in Beijing. London's easy because of the red phone box, but Paris it's picking up because of the architectural elements on some of these windows and doors. Los Angeles, that's probably one of the famous beaches. Sydney Opera House, again, easy to do. So and Statue of Liberty in New York. So, but it's doing very well, and there is no geolocation data here. It's purely working this out from the images themselves. Okay, so what I want to show you now is a demo. This came from some Nvidia researchers. I'll just play the first up to when they start manipulating the scene, just to show you how some of these machine learning models can run in real time, and they can convert with pretty much eerie accuracy one setting, one scene into another scene, and you start to wonder which is real and which is fake, which has real implications for us as you head into elections and all kinds of things. So let's play about the first 30 or 40 seconds of this.
Rendering photorealistic images using a standard graphics pipeline is complex. What if we could render images with a generative network instead? Starting with high-level labels that are much easier to create and edit, we present a generative adversarial framework for synthesizing 2K photorealistic images. To show the advantage of this approach, we provide an interactive interface for users to quickly edit objects in the scene. Let's try out our tools. We can select different colors for the car, or choose diverse textures for the road. We can also remove objects by replacing the existing labels with different ones. For example, replacing the trees with buildings, or cars with roads. Moreover, we can add new objects to the scene, like inserting a new car at a particular location with the desired object size. Finally, we can just paint on the label map to create novel scenes, like adding more trees into the image. Note that these shapes, colors, and textures are completely learned from the models without having any human intervention or handcrafted filters.
Okay, so that's kind of computer vision demo one. What's exciting there is the high quality nature of what they're able to produce, and they're able to produce that in near real time. The next one I want to show you is where a guy kind of hacked into his Tesla in France and was able to pick out the real-time segmentation that a Tesla is performing as you drive it. So this data is never offered up to the user. You couldn't make any use of it, and you'll see why in a second. But it's really interesting to look at to see the capability of the Tesla platform. So the compute power running inside a Tesla pretty much far exceeds anything in any other automotive platform. So let's take a look and see what it's doing as you're driving. This is going through Paris. So there's no audio on this one, but I think you can see the detailed ability of the neural network model to build up a really comprehensive picture of what's going on. So it's picking up everything that's moving, pedestrians, cars, everything. So, and if they're able to do this, but still not able to produce a fully self-driving vehicle at the top level that we want to get to, and they haven't, nobody has. It's still very unsafe to leave that to the machine learning model. It just shows you how hard the problem is to be able to solve the problem of driving in all settings: road conditions, weather conditions, nighttime, daytime, you name it. So that's just a a little peek under the hood of Tesla. And the last thing I want to talk about is the ability to generate high quality audio. So different domain, and this is Tacotron, which came out from Google. It's at least 2 years old now, but typically models that are 2 years old is what we're seeing in production now as they get fully productionized and all of the wrinkles ironed out. So the text and the audio you're about to hear is completely generated from unseen text by this model. So let's listen to the quality.
Generative adversarial network or variational autoencoder.
And the next example, this one's a bit of a tongue twister.
Basilar membrane and otolaryngology are not autocorrelations.
So high quality, and that's far different and of a far higher quality than maybe we were used to for similar systems in the past. Interesting on this page, if we go down to the bottom, you're able to play a game where you can try and see, can you pick out the human from the machine? So let's just use one of these examples. They've got 4 or 5. So example number 1.
She earned a doctorate in sociology at Columbia University.
So is that the machine or the human? And here's the example number 2.
She earned a doctorate in sociology at Columbia University.
And that's, they are so close. I think that's, pretty exciting to show what the future sounds like. And clear implications in business. So, what can we do now for personalized interactions with customers? Not just chatbots in the text domain, but, real world natural language parsing, semantic analysis, real-time conversations with somebody who sounds and acts like a human. That's on the way. Okay, so with that broad introduction to machine learning and some of the exciting things and developments that we've seen over the past number of years, let's drill into Webgains and let's talk about affiliate discovery for the Webgains network. So we ran a series of workshops about a year ago, and we came up with lots of ideas, and actually we have a pretty detailed product roadmap on how to implement those ideas. But one idea kept recurring over and over and over again. And at its heart, Webgains is a network. So we want to amplify things like the network effect. We want to be able to connect the most appropriate publishers with the most appropriate merchants. So Webgains is interesting. It's what we call a 2-color network. So you've got 2 different types of nodes in that network. And affiliate discovery came up. It wasn't called that at the time. It had an internal name. But the idea of being able to connect publishers with merchants recurred over and over and over again. It almost enables everything else that we want to do in the network. So we want to be able to give highly relevant and vetted, in ranked order, recommendations to join merchant programs, to affiliates. So that will help us to maintain and grow the network. It will really improve network diversity, which is a key goal of ours, and it'll help merchant sales and publisher commissions, with the bottom line. So this is the first of multiple modules powered by machine learning that we're launching. So it's the focus of this presentation. Let's dig into it in a bit more detail. So here's a really simple visualization of the Webgains network. So again, it's a 2-color network, as we said. On the left-hand side, we have all of our merchant programs, and we are able to cluster these merchant programs using all kinds of different features. So you can imagine we can do it by their network of residents, so UK, Germany, France, also by what they sell. We might also do it based on the particular brands they sell. There's many different ways we can slice and dice it. But we cluster these merchant programs. And on the right-hand side, we have many, many more publisher campaigns. We have about 2 orders of magnitude more publisher campaigns than we do merchants. So it's a really lopsided network in that regard. And we can cluster those campaigns in the same way. And so these black lines indicate pre-existing links between programs and campaigns. And so in a nutshell, here's the challenge for affiliate discovery. If I'm going to create one new link between an existing merchant program and either a new or existing publisher campaign, where should I connect that link? Where should I create that link and connect those 2 people together? And we keep asking that question over and over again until we've built enough links that we've satisfied our goal of diversity and creating the next set of really highly relevant links. So hopefully, when we draw it out like this, it looks like a simple problem. But to solve that problem using machine learning requires a lot of heavy lifting. So the two elements of machine learning and information retrieval that we drew heavily from, really I would say it's the core two central planks of affiliate discovery, is the research on recommender systems and then search in information retrieval. So when we recommend, and all of these systems here, so from whether it's Netflix, if you're a Netflix user or Amazon Prime Video, you see it every day when you log in at your home screen. So every major e-commerce platform uses recommender systems, and they're designed to solve not a flaw, but a really important use case in e-commerce and in consumption of content, which when I see you for the first time, what's the best thing I can offer to you right now? Bearing in mind that I know very little about you. So that's the cold start problem. And then the second time I see you, now I know more, but I still want to be able to offer you some recommendations without you, the user, having to do anything at all. So if I've done my job and if I've learned about your business, so whether your merchant program or you as a publisher / affiliate, I should be able to make some reasoned calculations about appropriate links to suggest to you. So that's the recommendation side of it. But we also wanted to include search. So you can say, well, I really want to find this publisher. So we built a really high-powered search to complement the recommender side of the engine. So again, it's the blended combination of recommendation plus search, which is at the core of affiliate discovery. So let's consider affiliate discovery from two angles. First of all, the publisher. So as I said, we have many more publishers than merchant programs. That's true for all affiliate marketing networks. And we've attempted to segment here the most important elements that we use to create pretty much a unique fingerprint for each publisher. So let's start on the left. These are count-based statistics, typically calculated over a window of time. So, and they're all about measuring popularity. So that would be unique visits to a URL from the entire world, also from a country code if we're interested in particular country networks. We're interested in how visits vary over time. So what's the variance, standard deviation of those statistics? And then two click-through ratios. So first of all, views to clicks, if a publisher is using views as well as clicks, and second, clicks to buys. This is just a small sample of the popularity stats that we use, but you can see we're building up a picture of popularity / activity. On the right-hand side, it's financial. So what kind of things do you sell as a publisher? So what are the individual product SKUs that you sell? What do they roll up into as far as a merchant theme goes? What's the average basket value? And is that highly variable or is that really focused in a narrow range? This is true for all of these boxes, all these categories, but I'll call out here. All new joiners to the network get credit for a defined period of time. And again, that's to get around the cold start problem. So when you join the network for the first time, we won't have data on some of these metrics. So we don't want to say, okay, you've sold nothing, therefore you're an ineffective publisher. That's not what the model does. The model is smart enough to be able to allocate a window of time for publishers to get up to speed, join relevant programs, and start generating transactions. The bottom category here is really important, as you'll see, because I'm going to do a deeper dive into this in the next couple of slides. So we really care about what the publisher is trying to say to us and to say to the merchants programs that are enlisted on the network. So what are the topics that you're talking about? So who are you trying to reach when you're writing content on your video blog or on your social media channels or on your website? Who is it that you're trying to talk to? And are we able to infer a relationship between those people and the merchant programs? Because if we can do that, we've cracked it. That's the heart of it. And how fresh is that content? What languages is that content written in? So who are you trying to appeal to? Technical SEO, it's important for Google and Bing and other search engines. It's important for us as well. And really just trying to figure out what conversation you're trying to have with your users and the consumers of your content. We take all of this and more. So on the publisher side of the equation, we end up at the moment with about 300 individual features that we feed into our machine learning model. So quite a few. And we also perform peer comparison and benchmarking. And that's not to say bigger is better, because it's not. In some cases, somebody may have a smaller number of unique visits, but they may have excellent, really specific content for a merchant program. There are many examples of that. So the Webgains network is highly specific in some areas and has some very wide publishers in others. So peer comparison helps us to build up, I would say, a number of league tables. So freshness, specificity, the quality of content, size of the publisher. And it's not about getting the number one spot in all of those league tables. It just helps us to understand more about the publisher. So let's flick it and let's say, well, what do we do on the merchant program side? So we need to do this on both sides of the equation to be able to generate the matches. So it's broadly similar. So we have popularity stats for a merchant program, again, over a defined window of time, so temporal. Here we're looking at their popularity within our network. What's the overall aggregate view on publishers this program tends to attract? So, which is a very different metric than on the publisher side. Unique visits, again, the variance and the CTR ratio that we talked about earlier. On the right-hand side, the similar financial stats again. Here, a big difference on the merchant program side is we receive a large number of product feeds, and we're really starting to make good use of that data. There's some excellent, highly organized data in there that we've been able to extract. Actually, it forms the basis of an upcoming module we're going to release soon. But we're able to understand what the merchant program wants to sell. So what do they have in stock? Who are they trying to reach on their side? That's their side of the conversation. Okay, so I said I was going to do a deeper dive into content topics, and so let's do that now. So I keep using the word conversation, and because as we built Affiliate Discovery, that's what it was uncovering. It was uncovering all of these conversations that were ongoing between merchant programs and campaigns on the network, and ultimately the end users who purchase. And if those conversations are well understood on both sides, hey presto, we get conversions, we get great traffic, and that traffic converts. If it's not, then we don't. So we employed natural language parsing, NLP, clustering topic modeling. We invested a lot of time in our machine learning models here. And ultimately, what we call the conversation or topic ends up containing multiple values that speak to things like brand, tone, message, all of the things that you implicitly think about every day in marketing. And we've tried to codify it into this part of the system. Topics are dynamic because they change over time. So travel is a great example of that. So what travel is trying to sell in the run-up to summer is very different to what it's trying to sell in the run-up to ski season. And that's also true for Black Friday, releases of new mobile phones, releases of new content, new films. So topics are able to change over time, and we generate topics continuously in the system. We calculate hundreds of topics per language, and right now we use the top 3. So the way our model works is every publisher is able to belong to hundreds of topics, but we found in our testing and tweaking of the hyperparameters, the top 3 gave us the best results. So that's what we use in the system. So here's some examples of some topics. I know this is a kind of a dense slide. I just want to talk about a couple of interesting examples here. So cycling picks up all of the cycling related stuff that you'd expect, and cars / driving. Here especially, it's interesting with cars. It picks up all of the makes and models. Certainly the makes. That's highly correlated with belonging to this topic. We've got a good number of merchant programs in the food domain on the network, and I want to talk about. We do some fine grained separation of topic tokens. So here's food 1, which is talking about restaurants, eating out, pizzas, things like that. Sometimes you get like outliers like denture, chef, and so that would appeal to a certain type of merchant program and publisher. And food topic number 2 is about baking at home. So you can see it's like about recipes, cooking, cakes, and it's I would say probably sweeter. If you look at chocolate cake, sugar, than food topic number 1. So we're able to, and these are not manually created. these are all automatically built from our data set. So these are the topics that our publishers and our programs are actively talking about in the network. Some examples here on fashion. So the first one is much more built around brands, as you can see there. So Burberry, Alexander, Gucci, and the second is more generic. So it's more about at the moment, obviously, everyone's selling summer, trending into autumn, and this is about general fashion lifestyle in those seasons. There's an example, the same fashion, a similar fashion topic for German, just to show that we do multi-language, and last one there is fitness. So hopefully this gives you an idea for the kind of segmentation we're performing around the publisher content and also the product feeds. So in any machine learning problem, what we end up looking at on the server side as we're building this is how big is the data, because that really tells you how much computing resource you need and how much time you need to train and retrain the models. And Webgains is not small. So when we start, we have 691 million candidates at system start time. We can apply some standard filters, and we end up what we call our plausible candidates. When we multiply out all of the possible combinations between merchant programs on one side and all of our campaigns on the other, is 76.5 million. So still large, but now this is manageable. So we're able to run this through and generate using reasonable compute resource and reasonable runtime. So after we've matched and grade, we end up using the circa 30 features on the merchant program side and 300 features on the publisher campaign side, and finally we recommend. So at the recommendation stage in the pipeline, we're really homing in on just the top 200 or 300 per program that we think are going to be relevant, because we want to find that needle in the haystack for the programs and for the affiliates. Hopefully everything's clear as we but and let's use a short worked example to really try and bring home how the system works. So very obvious domain. Here we've got a merchant who specializes in not just computing and mobile. So standard computers, laptops, tablets, and mobile phones and accessories. So you can envisage any number of these merchants online. Here's a high quality one. Again, standard. They're pretty much segmenting their product offering as you would expect. So this is nothing unusual here. So what did we generate for this merchant program in terms of topics? So we assigned many topics, but we used the top 3. So on the first, you can see that we're picking up. We think they're predominantly about computers and laptops, and these keywords here will show you what's going on there. All of these keywords are highly correlated and relevant to that topic. Second, we picked up mobile phones. So now you're moving into a different topic. So very different. Samsung, Apple, Huawei, iPhone, Sony HTC. And third is components. So the accessories, the USB accessories, cables, wireless, camera, gadgets, Bluetooth. And so using what I would say is a pretty simple premise, which is the mapping of topics, we've done a pretty good job in providing nearly complete coverage over this merchant program's product feed. And this particular merchant program has a very large product feed, so it's a good use case. So on top of that, so topics only represent 3 of the 300 features that we use, don't forget. So we overlay all of the other features that we generated from the traffic stats, from the financial stats, and all the other content features that we use to build up a complete picture and then narrow down to try and find that needle in the haystack. Okay, so this slide might come out a little bit small, but I think we'll be able to zoom in on it. These are the recommendations for topic number 1, and we've got, you can see these are all highly relevant, and if we look at the themes and the number of visits, these should all be able to generate good qualified traffic for that topic. Looking at topic number 2, very different publishers are showing up here. So they're not in the same space at all. But the merchant is able to slice and dice and say, well, okay, I really want to go for some mobile campaigns now in the run up to, let's say, the release of the next iPhone or the next Google phone, whatever it might be. But then coming up to Christmas time, I'm going to switch back to more traditional laptops and tablets. So, in summary, we've built the first of multiple machine learning modules and put it live in the Webgains platform for the use of our merchants and our affiliates. At its core, it is a blended recommendation and search engine combined. But in order for us to be able to surface that up in the user interface, it's using multiple machine learning models and multiple machine learning techniques behind the scenes, all built around the idea of these conversations, these tens of thousands, hundreds of thousands of conversations happening daily within the Webgains network. We've really worked hard to try and distill down the massive number of potential plausible candidates to the candidates that really matter for a specific pairing of program and affiliate candidates. So we hope you like it. We look forward to receiving your feedback. There's more coming, more modules, more updates, so stay tuned. Thank you.